Hey, Calculus 2 students, welcome to this Going Deeper video on cosecant cotangent type integrals. Now, as we're considering trigonometric integrals in class, you probably noticed we've got our sine cosine type trigonometric integrals and our secant tangent type trigonometric integrals. And you might recognize, hey, there's kind of a slot there for a third type of trigonometric integrals, and that is our cosecant cotangent type. And yeah, sure enough, that is a thing. They are integrals of the form cosecant to the m of x times cotangent to the n of x dx. So very similar to the other two types. And in fact, these can be evaluated using similar strategies to those that are used for the other two types. Nonetheless, cosecant cotangent type integrals, they do not get a lot of press time. They don't have much time in the spotlight typically, and you might wonder, why is that? Well, there are some reasons for that we'll get into that I see as likely reasons. One thing is, a lot of the strategies are the same. Pythagorean identity, again, is a big contributor to that. And the third form of the Pythagorean identity is 1 plus cotangent squared x equals cosecant squared x. So you can, again, obtain this one from your standard sine squared plus cosine squared equals 1 by dividing all three terms. In this case, you would divide all three terms by sine squared x to get this version of the Pythagorean identity. A lot of the same strategy and so forth. Okay, so these certainly do still come up. You'll see some of them in exercises and so forth. So you do need to know how to do them. But the presumption is you'll be able to figure it out because it's kind of just like the others. And that's actually one of our possible reasons here. But there are some other things I think contribute as well. First of all, if you've got cosecants and cotangents, you can rewrite that. Maybe in terms of sines and cosines, or even in terms of secants and tangents, but you can certainly do that. And then the question is, are you going to get an integral that, oh, this fits the patterns that we know how to work with of those other two types? And sometimes that happens. A reason two here, I think, has to do with another method of integration, another integration technique called trigonometric substitution. Now, that method is an optional method for our course. It's in section 7.3. And because we have so much mandatory stuff that we are trying to cram into our course, anything optional, I figure, let's just push it aside, even though it would be fun to do. It'd be interesting and challenging, but we've got enough on our plate as it is. But when you do trigonometric substitution, the goal there is to end up with the first goal anyway, is to end up with a trigonometric integral of the type that we are dealing with in this section. And from trigonometric substitution, you always get either a sine, you can always get either a sine, cosine, or secant tangent type. And so for trigonometric substitution purposes, the cosecant cotangent type doesn't really come up. And then the third reason is just what I mentioned earlier, that, well, cosecant cotangent, it's pretty parallel to secant tangent, so maybe we don't need to take the class time or whatever to hash through again how to do this when it's going to be like a mirror image of something that you have already seen. Okay, so those are some of the reasons, but nonetheless, let's see how this works. Okay, you should still be able to do integrals of this type. You'll see them come up. And that is particularly true of the cosecant and cotangent functions themselves. Okay, although they are basic functions, they're not on our list of basic antiderivative formulas. So there is some work involved. But once you know how to do the integrals of secant and tangent themselves, you will definitely see a lot of parallels with cosecant and cotangent. Okay, so let's take a look at one example of a cosecant cotangent type integral. What about the integral of cotangent x over cosecant cubed x dx. Okay, so what are some strategies that we could use towards evaluating this? Let's see if we can come up with two such strategies. Okay, so for the first strategy, I'm going to imagine that this is like a secant tangent type integral. And one of the things that so there are two things that we look to hold out for our du in those situations. For a cosecant cotangent type integral, it would be either a cosecant squared x, or it would be a cosecant x cotangent x. Okay, now in this integral, a little bit of a twist is that we don't really seem to have either one of those, and so let's get it in there, right? Just because something's not in there doesn't mean that we can't somehow finagle it in there. So for option one, what I'm going to do here is take that original integral and multiply it by 1 in a strategic way to get one of those factors in there that are of the type that I want. Okay, so let's see if I can get this to change color. Always a dicey proposition. There it is. Okay, so let's take the integral, and we have a cotangent x in the numerator. If we had a cosecant x, that would be very helpful, so let's put it there. But as you know, if you multiply the numerator of a fraction by something, you've got to multiply the denominator of the fraction by that same thing. And so there we go. And if we want to make this look even, well, okay, maybe we'll just leave it like that. Okay, so let's see if I can switch back to my ordinary color here. Oh, nope, not as easy as it looks. Okay, so at this stage, we are going to have cosecant x cotangent x dx in the numerator, and then in the denominator, we will have cosecant to the fourth of x. Okay, well, now we're good to go. Again, taking that parallel with the secant tangent type integrals, here we could let u be cosecant x, and this is really promising because the derivative of cosecant x is cosecant x cotangent x, and we see that in the numerator. Okay, so there's a minus sign as well that will pop in there that we have to deal with. One way to deal with it, I thought about doing this earlier, but we could put a minus sign outside the integral and a minus sign inside the integral. Again, those balance out, and now we would have the exact derivative of cosecant x in our numerator. Okay, so that's option one. Looks pretty promising. I think I'm covering up my... Yeah, so which option do you think will be easiest or best is another part of the consideration here. So let's take a look at another option, another way to think about this. And for this strategy, I'm going to try converting to sines and cosines. Okay, so let's just put a 1 here. This is option 1. Okay, option 2, let's take our original integral, and this time I'm going to say, well, cotangent x, I know that that is cosine x over sine x, also the key to integrating cotangent function itself, by the way. And then I've got 1 over cosecant cubed x. Well, okay, that would be 1 over sine cubed x. I'll tell you what, let's write it this way. 1 over sine x. Let's see, 1 over cosecant x cubed. Okay, well, then we got our dx out here, of course. Now, you know that 1 over cosecant x, one of our basic trig identities, says, oh, that's just sine x. So another way to write what we've got here is cosine x over sine x times sine cubed x dx. Okay, And there again, it looks like we're well on our way to something. This should be a doable sine cosine type integral. Okay, so now what you can think about is, what would you do here? Suppose you had these two options. Maybe you could think of more options. But if you had these two options, which option would you pick? You can think about that for a second. Pause it if you like. Okay, well, I'm going to go for option 2, because if I am aiming for simplicity, which is often a good thing to aim for when doing integrals, I think that the sine cosine situation is going to be even just a little more, if nothing else, a little more familiar, a little nicer to deal with. So let's take this onto a different screen here. Actually, let's rewrite it one more time, because you've probably been, screaming at the screen to do this anyway. We can cancel sine from the numerator and denominator and just have sine squared x times cosine x dx. Okay, now for more space, let's go to the next slide. Okay, so using our chosen method here, which was option 2, let's go ahead and finish off this integral. So our original integral, again, cotangent x over cosecant cubed x dx. We got that rewritten in terms of sines and cosines, and it was sine squared x cosine x dx. Okay, I believe that's what we ended up with as we were working on it on the previous screen. Okay, so this is a typical, not particularly hard sine cosine type integral. You know that here we just can go ahead and take u to be sine x, since the power on cosine is odd. It's got a first power on it really there, so du then will be cosine x dx, and that is just sitting right there waiting to be used, so that is perfect. Okay, sine squared x will become u squared. Cosine x dx becomes du. All right, now we got an integral that we can do. It fits our power rule formulation. It'll just be u cubed over 3. Indefinite integral, so we got to put the plus c. And then we're not quite done yet. We want to put the sine back in there. So let's put this back in as sine cubed x over 3 plus c. And voila. Okay, answer is not in terms of cotangents and cosecants, but that's okay. It's actually probably a little simpler than that, which is great. Okay, so there's our answer. Again, this is the answer that we got using option 2, converting into sines and cosines. Good thing for you to try if you want to follow up on this, take it a little further, is to go back to option 1. Try to finish off option 1 yourself, see if you can evaluate the integral using that approach, and then take a look, if so, at the result that you get. Compare it to what we got with option 2. Is your result the same? Okay, if it doesn't look the same right away, can you reason your way through to seeing whether it is in fact an equivalent expression? Okay, hope you enjoyed this Going Deeper video, and I'll see you again soon.